Hello, and welcome to Lecture 1 of Gauss's Law in Phys 1204. Symmetry has been a theme in both Phys 1104 and in this course, but it's been a while since we've looked at it explicitly, and in this unit it's going to be one of the central ideas. So this lecture is all about symmetry. We saw way back at the very beginning of Phys 1104 that the meaning of symmetry mathematically is the group of geometric transformations which leave an object unchanged. So for example, we can talk about the symmetries of this happy face. If you flip it left to right, it remains unchanged. It looks exactly like it did before you did the left-right flip. And so we say it is symmetric under that geometric transformation. On the other hand, if you flip it top to bottom, or if you rotate it 90 degrees clockwise, it doesn't look the same. And so those are not symmetries of the happy face. We talk more formally about these symmetries in terms of reflections and rotations. So we can reflect the happy face through a mirror line M, and it will be symmetric under that transformation, but it is not symmetric under a reflection through this other mirror line N, or symmetric under rotations about this axis S, which is perpendicular to the screen. So these are examples of two possible geometric transformations that we can talk about as symmetries of an object, reflection and rotation. Notice that in 2 dimensions, the reflection through the mirror line M is the same as what you would have if you rotate 180 degrees about an axis vertically down through the happy face, and that both of these are symmetries of this 2-dimensional happy face. However, if you make it a 3-dimensional happy face, such as a Pinocchio face with a big long nose sticking out of the screen, now it's symmetric under this reflection, although we now have to talk about a mirror plane M, not a mirror line. However, it's not symmetric under this rotation about the axis S anymore, because it takes the nose, which was sticking out of the screen, and rotates it so that it's sticking into the screen. Different objects have different symmetries, of course, so instead of the familiar happy face, let's talk about this happy face of some alien species that has a mouth in the middle of its face surrounded by 4 eyes. This is symmetric under reflections through the mirror line M and the mirror line N, and 90 and 180 and 270 degree rotations about the axis S. So note that it has more symmetries than the familiar human happy face, and so we would say that this object is more symmetric or has higher symmetry. Often it's useful to refer symmetries to a set of axes. So for this set of axes that I've just defined, I could say that this alien happy face is symmetric under reflections through the YZ plane and rotations about the Z axis. But the real reason I just introduced axes as a way of talking about symmetry is so that I can talk about one more type of symmetry which this alien happy face doesn't have, and that's translational symmetry. If we translate the happy face along the x-axis, now it's changed. It's in a different location from where it was before, and that counts as a change. So this happy face does not have symmetry under translations. You might be having a hard time picturing how any object can have translational symmetry. After all, if you shift something left or right, it's always going to look different, isn't it? Well, that's true for real objects, but there is one way to have translational symmetry, and it's that the object has to be infinite in size. So let's think of this set of lines that go on forever. Well, note they're symmetric in a reflection through the YZ plane, but they're also symmetric if you translate them along the x-axis. How would you know that these lines have translated along the x-axis? Every part of each line looks exactly like every other part, and they have no ends, so you can't see that the ends have moved. On the other hand, they do not have a symmetry under translation along the y-axis. We've already discussed in the electric fields unit that while of course no real object is infinite, Things like infinitely long, thin lines are often reasonable approximations for real objects when we're finding the electric fields due to them. So we're very interested in symmetries of objects like this. So let's think about an infinitely long, thin wire that runs along the x-axis. This is a very highly symmetric object. So you, before you go on to the next lecture, should think about which of these are symmetries of this object. And I will say not all of them are, but many of them are.